Welcome back to the course entitled Elementary Electrochemistry. In the previous class, we started discussing about some of the applications of conductometric titrations or the measurement of conductance. And if you remember that I had given you a couple of few problems, or I had asked you to try to draw the titration plots for some proposed experiments. So the first one that you are supposed to do is a mixture of HCl plus acetic acid versus NaOH. So how it should look like? Without going into much of the details, I am going to draw the plot and then discuss why it should be like that. See, when we have a mixture of strong acid and weak acid, the strong acid is completely dissociated, and because of that, weak acid dissociation is further suppressed because of common ion effect. So the weak acid remains nearly in undissociated state. So the conductance that you get is mostly because of the conductance given by HCl. So when we are titrating it with NaOH, it is now just a strong acid, strong base titration. With addition of more and more NaOH, the conductance should decrease sharply till the H plus ions coming from HCl is left. When this HCl concentration is reducing, the dissociation of acetic acid increases, so that near the equivalence point, this straight line starts to deviate from linearity. And beyond the equivalence point for HCl, the graph or the conductance tends to increase, because now acetic acid is decomposing and producing more H plus ions before the neutralization by another amount of NaOH. So you add NaOH, H plus is removed, you let it equilibrate, some more H plus is generated, the conductance increases. So this continues till acetic acid is there in solution. And when acetic acid is again getting totally consumed, NaOH takes over, so you get a plot like this. So I have marked three zones which are mainly dealt by HCl, acetic acid and NaOH. So in this condition, one has to draw or extend this straight line like this, draw a tangent on that line and draw a tangent on this line. So this point gives you the equivalence point for HCl. This point gives you the equivalence point for acetic acid. If this is V1 and this is V2, V2 minus V1 is the bullet reading for acetic acid, and V1 is for HCl. Hope you can understand this. So next one what I gave is number 2 is a strong acid HCl plus a weak acid acetic acid versus a weak base ammonium hydroxide. So as usual, the conductance initially will be governed by HCl. And with addition of ammonium hydroxide, the conductance will continuously decrease till about the equivalence point. Near to the equivalence point, when the acetic acid starts to decompose, it will curve around, it will go up, and then when acetic acid is also consumed, NH4OH is there, there will be a change of slope. So two different slope changes will be evident. You draw a tangent here, you draw a tangent there, you draw a tangent here, and you draw a tangent there. So this will indicate V1, this will be V2. V1 is for HCl, V2 minus V1 is for acetic acid, right? So by doing one titration using ammonium hydroxide, one can do this. Only thing you need to remember is this should be 10 to 100 times more concentrated. Similarly, ammonium hydroxide should be 10 to 100 times more concentrated, so that the dilution effect is removed. You may have about 100 ml of this solution, and you will need about 1 to 1.5 ml of NOH. In this case, again for 100 ml here, you will need about 1 to 1.5 ml of that solution, right, of ammonium hydroxide solution. So the third problem that I gave you is a mixture of three compounds. HCl plus NH4Cl plus KCl. I wanted to know the concentrations of these three components individually. So you can see that this is a strong acid, this is a salt of strong acid plus weak base, and this is a salt of strong acid plus strong base. One thing is common here is the anion chloride. So one can do one titration using strong base NaOH to get the concentration of HCl and NH4Cl, and one can do a second titration with AgNO3 to get total chloride concentration, and from that one can subtract the concentrations of this HCl and ammonium chloride and get the concentration of KCl. So for the first titration, the conductance versus volume of NaOH. As usual, initially it will decrease. After all HCl is consumed, NH4Cl, being a salt of strong acid weak base, will dissociate to produce the corresponding HCl and weak base ammonium hydroxide. So you are using NaOH, so that will consume the HCl generated, and then the plot will go like this, and at some point after that is consumed, it will be like that. So this V1 and this V2 will be the two endpoints. V1 will indicate the endpoint for HCl, and V2 minus V1 will be the endpoint for ammonium chloride. V2 minus V1 will be the endpoint for ammonium chloride, right? And then the second titration, as you can understand, which we have also discussed in the previous lecture, the conductance of the solution will be measured when doing the titration with while doing the titration with silver nitrate solution. So in this case, the chloride ion is replaced by nitrate, which has about the same ionic lip conductivity, so it will not change and then it will increase. So this will give you the volume of total chloride. This V1 will give you the concentration of total chloride, and then from that one can determine the concentration of KCl independently. In addition to these different conductometric titrations, one can also determine the degree of dissociation of weak electrolytes. So for this, we need to understand the theory behind it. So in case of a very dilute solution of a weak electrolyte, the dissociation is very less, which essentially means the number of ions in the solution is very less. And hence the inter-ionic interaction is also negligible, right? We increase dilution. With increase in dilution, dissociation increases, and hence the equivalent conductance increases and reaches a limiting value, which we know we write as lambda 0. So now let us assume that 1 gram equivalent of an electrolyte produces n plus number of cations and n minus number of anions at infinite dilution, and the charge of each cation is Z plus, and that of each anion is N minus. So then at infinite dilution, lambda 0 is nothing but N plus Z plus E u is the speed of the cation, plus n minus z minus ev, where the v is the velocity of the anion. We write this equation as number 1. If we assume now that the degree of dissociation is alpha at concentration C, then the equivalent conductance at concentration C, which I am writing as lambda C, would be the following. Lambda C will be equal to alpha n plus z plus EU plus alpha n minus z minus EV. So we write this as 2. So now this alpha n plus and alpha n minus are the number of ions or number of cations in the concentration C. So now if you divide equation 2 by equation number 1. So what I am doing is lambda C by lambda 0. We see that if I take alpha out, it is equal to alpha. Or one can simply write alpha equal to conductance at or equivalent conductance at concentration C divided by lambda 0, which is nothing but L0C plus L0A. So one can determine lambda C at a concentration C and use the values of L0C and L0A to calculate degree of dissociation alpha using this expression, right? So what we know is that if I have a weak acid HA, which is dissociating as H plus plus A minus, at a concentration C, this is the concentration of H plus, this is the concentration of A minus, and this is the concentration of C, HA, undissociated HA. So one can write the dissociation constant K alpha equal to concentration of H plus into concentration of A minus divided by concentration of HA, which is nothing but K alpha is equal to alpha C into alpha C divided by alpha C into 1 minus alpha, which is equal to alpha square C by 1 minus alpha. Now, in the previous slide we have learned that alpha is equal to lambda C by lambda 0. So when you replace alpha by lambda C by lambda 0, you get K alpha equal to lambda C by lambda 0 square C divided by 1 minus lambda C by lambda 0, or by simplification, lambda C square C divided by lambda 0 into lambda 0 minus lambda C. So once again, by determining the values of lambda C and calculating the value of lambda 0 from the corresponding L0A plus L0C, one can calculate the dissociation constant of a weak acid efficiently, right? Now, in general, alpha is very small. It is so small that 1 minus alpha can nearly be equated to 1. So, this K alpha can be written as simply alpha squared C, or alpha is nothing but square root of K alpha by C. So one can calculate the value of alpha also used by determining the value of K alpha from here and placing it in this equation as usual, right? So this is how one can easily determine the dissociation constant and degree of dissociation of a weak electrolyte. So here I am to give you one problem. The equivalent conductance of 0.014 normal solution of chloroacetic acid is 109.0 mole centimeter square, and the ion conductances are 40.2 and 349.8 for the anion and cation. Then calculate the degree of dissociation and dissociation constant of chloroacetic acid. Right? So it is possible to do this calculation using the method that I have just discussed today. So with this we will conclude this lecture, and I will continue from here in the next class. Thank you.